Alright, hello everyone. I'm titling this presentation A Reason for Pointers with a subtitle, A Step Back to Sprint Forward. And my purpose in this video is going to be to try to give you maybe a little bit more thorough of a foundation upon which to understand pointers, what they are, what they can be used for, and so forth. Many textbooks don't do a great job, I guess, of giving the motivation for pointers. They tend to just say, here's what they are, here's what they do. And so in my introduction to pointers, what I want to do is give you a case scenario that's actually a very real one, in which we would want the capabilities pointers provide. And then I will explain what pointers are, how they work in the context of that problem. Then we will see how they make it possible for us to do cool things. Okay, so to begin with, I want to back up to some earlier topics we discussed, specifically the way that functions behave relative to memory. Okay, so you'll recall that when a function begins to execute, it gets a chunk of memory called a stack frame where all of its local variables live, right? And as functions are called then, additional stack frames are created where those functions have their variables and so forth. And again, there's this kind of stack-like behavior where the last thing placed on becomes the first thing to come off when said function finishes and so forth. Okay, so you'll recall we get that behavior kind of like the stack of plates in the cafeteria and so forth. Okay, so what I want to do is actually look at kind of a scenario where we've got these two hypothetical functions, fun1 and fun3, we'll work with in this case. Fun1 simply creates this int variable called an int, stores a 7 in it, and then calls, does some other stuff hypothetically, but at some point it calls fun3, sending in an int as a pass-by value argument. Once fun3 returns, then we will output the value of an int and return from fun1 as well. All that fun3 is going to do is take that value that it received, print it to the screen, then it's going to change this variable value to 42 before it returns. Now again, notice that that parameter int value that we see in the definition for fun3, that this is, again, it's a pass-by value parameter, so there's actually a local variable called value that gets initialized to the value of the argument when the function is called. Okay, so let's kind of clear up our memory diagram over here and make it reflect these specific functions a little better. Obviously, fun3 is not using a ton more memory than fun1, so I modified this to reflect that. So while fun1 was executing, we saw that an int was created and somewhere in memory, and it was initialized to the value 7. When fun3 is called, then there's this local variable, as I mentioned, value, the parameter, that's created, and its value, again, is initialized to the value of an int. So it gets a copy of an int, or the value in it, and is set to 7. Now, as we begin executing the code inside of this function, we see the cout statement wherein the value stored in value is going to be printed to the screen. So we see a 7. We go a little further and we see there's this assignment. So we're trying to change the value of the variable value to 42. And we see that happen on that local variable in memory. And then we hit the return statement. Okay, so recall that when that happens, we go back to where we'd finished executing in the previous function, and the memory being used by our current function, fun3, is given up, right? It's what's known as deallocated, and now it's available to be used for something else. We then continue executing in fun1, and we execute the cout statement, and we're printing an int to the screen, and so the value in that, which is still 7, shows up on the screen. So even though we messed around down in fun3 with value and changed it to 42, that had no effect on an int because value was a local copy of the value that was in an int when fun3 was called. Okay, so that's just a quick review on pass-by value. Let's go ahead and clean this up a bit and discuss a scenario in which, well, maybe we wanted fun3 to be able to change an int. And we, at this point, know that we can use pass-by reference to do that. So I've added the little and symbol down there to behind the type to that parameter value. And so now when fun3 gets called and it has this local variable, i.e. this parameter value, it's not going to receive a copy of the argument, but rather a reference to it. Okay, so I've got these stars here to just represent kind of some location that an int is stored at. Okay, and so it's going to be that location then that's stored in value, which kind of points back to the location of an int. It serves as a reference to it, and you can follow that reference and find the original argument. So when we execute this first line here with the cout statement then, and talk about value, we're not going to get the value stored inside of value, but rather we're going to follow that reference back to find an int, the original argument, and we're going to read its value. And so that's what's printed to the screen. So that's why we see the 7. In this case, not a copy of the 7, but the actual original that we chased down by following the reference. So then here on the next line where we're trying to assign value the number 42, again, the same thing's happening. It's a reference, and so we'll follow that reference back to the original argument, and that is what will be changed to 42. So then when we hit the return and jump back up, an int has now been changed locally inside of fun1, and it no longer has the 7, but it has the 42, and that's what will be printed to the screen. Okay, so this works because of this notion of pass by reference. But this capability, pass by reference, has not always been available, right? So in C++ we can do it, but in the language C, which C++ was built and based upon, or I should say it extended upon it, there was no such thing as pass by reference, and yet there was very much desire to do the same kind of thing, where a function could change or modify a variable that was declared in another function, one that had been called earlier. And so how on earth could this be done then, if we don't have pass by reference? Well, not surprisingly, the answer to this is pointers. Okay, pointers will make it so that we can do this. How? Well, first we need a good definition for a pointer. So this is the definition I want you to use, and I want you to burn this into your brain, especially the first part of this definition. A pointer is a variable. It's a variable, folks. It's not just an address. It's a variable, okay? Remember that. The pointer is a variable that stores an address. So the address itself is not the pointer. It's just an address. It's the variable that's containing it that we call a pointer. Of course, that address is some location in memory that we, for some reason, care about, okay? All right, so what's the syntax for this? How do we create these variables and work with them? These variables we call pointers. Well, let's look at creation first. The basic syntax is we provide a type, then a star, and then an identifier, followed by a semicolon, okay? Or if we want, we can initialize these just like other variables, but in general, you've got to have a semicolon in there somewhere, okay? So why do we need a type? Well, even though this variable, this pointer, is not going to store a value that we probably care about, it's going to point to a value that we care about, and we need to know what kind of value it is, right? So we need to know how to interpret the data that we will find at the location that the pointer is indicating. Okay, so that's why there's always going to be a type. Putting the star behind it tells the compiler, hey, this is actually a pointer. It's not a whatever, right? It's not an int or double or whatever. I'll point out also that this star doesn't necessarily have to sit right here. It could be placed right here next to the identifier. Okay, and at some other time we can have discussions about pros and cons of those two different placements, but it turns out that they both work. You'll generally see me do this and put it behind the type. Okay? All right, so for instance, if we wanted to create a pointer to an int, then we'd put int star and then the name of the pointer. I've called it an int pointer just for demonstration purposes, and we do the same kind of thing if it was a double or a string or whatever. We name the type, we put the star to say it's a pointer, and then the identifier. Okay, this raises the question, fine, I can store then an address and a pointer. How do I get the address in the first place? Well, we do that with this AND symbol. Okay, which is undoubtedly part of the reason that when we do pass by reference and we're dealing with these kinds of things, you see the AND symbol pop up because we're dealing with addresses. Okay, under the hood, that's the mechanism that has to be used for pass by reference to work, is some kind of mechanism for keeping track of an address. So we'll do the same thing. Let's look first at how we would assign a pointer then. So here I have a regular int variable that's storing the value 8. Let's say I'd like to point to that variable. I'd like to store its address. So first I need a pointer, so I've created one here just called an int pointer. And then I could assign it to contain the address of an int thusly. So I'd simply say an int pointer equals, okay, so we're doing assignment the same way we do with any other variable. But then to get the address of an int, I simply put that and symbol in front of it, and we would literally read that address of an int. So an int pointer is being assigned the address of an int. Okay, great. Now we will find that there are other situations in which we have an address provided to us in various ways, and then we want to store that address. And so in that case, we would use the assignment operator the same way, but maybe we didn't have to actually say address of with that and symbol and so forth. But this is how we would get the address of a particular variable whose identifier we know. Okay, so if, for instance, this was playing out while our program was running, maybe memory is set up here to the right, kind of the way I've diagrammed, and these numbers to the left of the rectangle there are meant to indicate addresses. So maybe we've got 0 up through kind of 800 going on there, right? So while our program is running, this line here might have caused an int to be created in memory and initialized to the value 8. And then we see that this line, wherein we declare an int pointer, would cause a piece of memory somewhere to be set aside for the variable an int pointer in the same way. And notice it has an address. I haven't indicated what it is, but it has its own address. Pointers are variables, so they have addresses, locations in memory too. Here I haven't initialized it, so I don't really know what value is being stored in it, but the next line here will cause us to say, okay, what's the address of an int? It's 500, so that's the value that gets stored in the pointer. Okay, fine. So we've got a pointer now that has an address in it. How can we use it? Well, one of the most common things we'll do with pointers is dereference them. What does that mean? Well, it means that we follow the pointer. We follow that address to that location in memory, and we actually work with whatever we find there. Okay, and it's the value or the information we find there that we care about. How do we do that? Well, let's take a quick look. So if I had a cout statement and I just used the name of the pointer, an int pointer, then it's going to be the value stored in the pointer that would show up on the screen. And so in this case, that's the value 500, the address of an int. Sometimes we want that. I'd say probably the majority of time, no. Most of the time we're not wanting to print an address to the screen. It would be that value at that location we care about. So if we want to follow that address in memory to the variable we're pointing at, and we'd like to get that value, and that's what we'd like to print to the screen. We indicate that simply by putting a star in front of the pointer. That tells the compiler at this point we want to dereference that pointer. We want you to follow it to that location in memory and get whatever you find there. So in this case, this would cause us to actually print a value 8 on the screen via that pointer and int pointer. Okay, so that's how we can read a value that's being pointed at by dereferencing the pointer. Turns out we can also write a value in the same way. So here we've said star and int pointer, we're saying dereference that pointer. So go to that location and assign it the value 15. Okay, so when that executes, then the value and int would be changed to a 15. And so when this line now prints the value that's being pointed at by an int pointer, we would actually see a 15 on the screen instead of an 8. Okay, so let's go back to this situation we were talking about before where we said, okay, what if we want to do this pass by reference stuff, but we didn't have pass by reference in the language? Well, if we have pointers, we can get the same kind of behavior. Let's see how. The first thing we want to do is clean this up to reflect using a pointer. So here you see fun3 is now using a parameter that's a pointer. It's an int pointer called value. So instead of pass by reference, we're going to use pass by value, but the value we're going to pass is going to be a pointer. Okay? So up here where we're calling fun3, you'll notice I needed to add that and symbol to say it's not the value of an int that I want to send, it's the address of an int that I want to use as an argument. So that's the thing that'll be copied then down into value. Okay, So, I got a little ahead of myself. Now for this to work properly, inside of fun3, where I'm using that value, let me back up here so you can see that again, where I'm using the variable value, I want to make sure I dereference it, where I'm, for instance, trying to print a value and then where I'm trying to make an assignment. So I've had to add that star in front of value in those locations where it's being used. And again, you saw I had to add address to an int where I made the function call. So now let's walk through this. So when fun1 is in execution, it initializes that variable an int to 7, and then we call fun3. So fun3 gets a stack frame, it's got some memory here, and that local variable, that parameter value, is sitting there, and it gets initialized then to the address of an int, the value that we passed in as an argument. So if an int was living at the address 804, I'm just making this up, then it's that address 804 that would be being stored in value. Now here, where we have the cout statement in fun3, and again, we're using value, but now we're dereferencing it. That means then that we'd follow that pointer back through memory. We'd find a value there. It's the value for an int, and that's the 7, and that's what would be printed to the screen. On the next line then, again, we're dereferencing values, so we would follow that pointer back through memory and change the value that's there, right? Change the information that's there. So our 7 gets changed to a 42. And then we return. So like before, we see the memory for fun3 deallocated, and we end up back here in fun1 where we're going to execute that cout. And once again, it's an int that's being, the value of an int is being printed to the screen, which we have updated to a 42, and so we see the 42 pop out on the screen. Okay, so this is just an example of how pointers can be useful. Pointers can be used to get the behavior we see when we use pass by reference if pass by reference isn't available. Now, some of you are sitting back thinking, I wonder if that's actually what happens when I do pass by reference. And yes, actually, that is what's going on, is the compiler is doing this work for you, right? Of passing in this address, storing it in a pointer, and doing all the dereference and all that other stuff. It just takes care of it for you so you don't have to worry about it. So in reality, you've been using pointers when you pass by reference all along. It's just that the compiler managed it for you. You didn't have to deal with all these stars and ampersands and so forth, right? And so this is cool. It's a nice feature, but now you know a little bit more about what's going on under the hood, and you've seen a demonstration of why pointers might be useful, something that they can do for us. As we move forward, we'll look at other examples. In fact, we're going to talk about dynamic memory allocation, which is a situation where we must use pointers also. But hopefully this little demonstration and discussion gave you a glimpse or another look, maybe a more stable context that you can work from when trying to understand pointers and their syntax. All right. Thanks, everyone. I'll talk to you later.